Welcome to The Explainer. Today, we're going to be looking at something that honestly sounds a little bit like science fiction, but I promise you it is pure mathematical reality. We're talking about how machines, vehicles, and software literally predict the future. Seriously, we're unpacking the fundamentals of state space modeling in engineering. So if you've ever wondered how an autonomous system knows exactly what to do next without a human telling it, you're absolutely going to love this. Here is a super quick look at a roadmap for today's Explainer. Predicting the future, defining the state space, upgrading classical physics, navigating the cosmos, filters and digital twins, and finally, the engineering cornerstone. We've got this complex math broken down into clear, manageable steps, so let's get into it. Section 1, Predicting the Future. Okay, let's dive into this. To really wrap our heads around state space modeling, we first have to ask, how exactly do machines predict the future? Well, imagine for a second that you're driving a car. At any given split second, you can describe that car using just a handful of specific metrics, right? Where is it located? How fast is it moving? Which direction is it pointing? How much fuel is left? If you can track those current conditions, and you know exactly how the driver is pressing the accelerator or turning the steering wheel, you can mathematically predict exactly what that car is going to do next. And you know, that incredibly simple driving analogy? That is the secret mathematical language being used across the board in modern engineering. State space models aren't just some abstract niche theory you learn and forget. They are the absolute foundation for spacecraft navigation, aircraft flight control, robotics, autonomous vehicles, AI, and digital twins. The big takeaway here is that rather than just describing what a system is doing right now in this very second, this model empowers engineers to look ahead and predict what it will do next. Section 2, Defining the state space. Let's take that familiar driving analogy we just used and build out our sandbox of engineering terms. First up, we have the dynamic system. A dynamic system is, well, exactly what it sounds like. A system whose behavior changes over time. Think of a satellite zipping around the Earth, a robot arm assembling a car, a battery charging up, or our vehicle accelerating down the highway. To predict the future of these dynamic systems, engineers need way more than just a snapshot. They need a rigorous model of how the entire system evolves. Now, what's really interesting about this slide is the concept of the state. The state is the absolute bare minimum set of variables you need to completely describe a system's current condition. You can kind of think of it as the system's active memory. So, for our moving car, the state might literally just be its position and its velocity. If we know those specific variables, we know everything we need to predict its future motion. Next up, we have the input. The input is simply what is actively influencing the system from the outside. These are the external actions or commands that force the system to evolve. In a car, it's you, the driver, pressing the gas pedal. In a spacecraft, it might be the engine firing or the physical torque from a reaction wheel. And finally, rounding this out, we have the output. The output is what we can actually physically measure from the system. It's the tangible result of that evolving state. We're talking about a GPS coordinate on your dashboard screen, the physical needle on a speedometer, camera images, or telemetry from a star tracker on a satellite. When you snap all those concepts together, you get this beautiful continuous cycle. Picture a spacecraft out on a mission. We start with the current state, where it is and how fast it's going. Then a control input happens, like a small thruster burst. This forces a change, creating a brand new state with a slightly altered trajectory. The onboard sensors measure this new output, and then the whole system just loops right back to the beginning. It just repeats this exact cycle over and over, continuously, for the entire mission. Section 3. Upgrading classical physics. Now, you might be wondering, why don't engineers just use standard physics equations? We already have those, right? Well, classical physics usually describes things using a whole bunch of separate differential equations. Think back to Newton's second law, force equals mass times acceleration. But if you have a highly complex machine, solving all those separate equations one by one is just agonizingly tedious. Actually, scratch that. It's virtually impossible to do quickly enough. State space models take all those messy equations and neatly bundle them into one compact, highly organized mathematical framework. It is absolutely perfect for computers to process, which makes it the go-to choice for digital simulation and modern navigation. Section 4, Navigating the Cosmos. Let's move to and see how this builds from a car on the highway to high-stakes spaceflight. This comparison is brilliant because it perfectly illustrates the universality of this math. Check this out. Top row, a car driving in a straight line uses position and velocity as its state, the gas pedal as its input, and the speedometer as its output. Bottom row, a high-tech CubeSat orbiting the Earth uses its X, Y, and Z coordinates and velocities for its state, gravity and thrusters for its inputs, and its onboard sensors for its outputs. It's the exact same mathematical framework, just applied to two wildly different machines. Because engineers can map out a spacecraft's variables so cleanly this way, the mission software can just relentlessly update the state vector. Every single second, the pull of gravity changes the spacecraft's velocity, which in turn obviously changes its position. By keeping track of this mathematically, we can predict exactly where that satellite is going to be minutes, hours, or even days from now. Without this specific state-space model, doing precise orbit prediction for our CubeSat, that would be almost completely impossible. Let's look at a life or death control system example. Imagine a spacecraft suddenly gets hit by something or malfunctions and begins tumbling wildly out of control. Instantly, onboard sensors detect this rogue rotation. The computer uses the state-space model to rapidly estimate the new current state. It then immediately fires back inputs, commands to the reaction wheels. Those wheels spin up, torque the spacecraft, slow the spin, and the state changes again. The sensors measure the new, slower rotation, and this rapid-fire feedback loop repeats dozens of times a second to literally save a multi-million-dollar mission. It's that continuous looping motif in action. Section 5. Filters and digital twins. So that continuous feedback loop we've been talking about, it powers two major modern engineering superpowers. One of the absolute biggest is the Kalman filter. The Kalman filter really just does two tasks over and over. First, it predicts the next state using the state-space model we built. Second, it corrects that prediction by checking the actual sensor measurements. Without a state-space model, there's literally no prediction to make. This simple two-step prediction and correction process is absolutely fundamental to how your phone's GPS works, how aircraft guide themselves to a runway, and how autonomous vehicles see the road. The other massive superpower is the digital twin. Modern digital twins are basically built entirely on state-space models. As a real physical system, say a jet engine, changes over time, its digital twin predicts what its future state will look like. Sensors on the physical engine send back updates, and the digital predictions get sharpened and refined. This lets engineers monitor and optimize insanely complex systems in real time, from thousands of miles away without ever touching them. Section 6. The engineering cornerstone. Wow, we've covered a ton of ground today. So the crucial point is this. Dynamic systems are always changing over time. The state describes the system's exact condition in a given moment. Inputs force that system to evolve. Outputs are the things we can actually measure. And state-space models are the brilliant mathematical frameworks that use the current state and inputs to accurately predict future behavior. Whether you're working on a tiny robot or a massive power grid, understanding how these elements interact is how engineers are building our autonomous future. I want to leave you with this monumental thought straight from the source text, because it really hits the nail on the head. A state tells you where a system is now. A state-space model tells you where it will be next. That simple predictive ability, neatly wrapped in an elegant mathematical package, that is exactly what makes this whole concept so incredibly powerful. It's this invisible mathematical heartbeat running constantly behind the scenes of our modern world. Knowing this, how much of your own digital life, the airplanes you fly in, the maps you rely on every single day, the autonomous tech you interact with, do you think is modeled this exact way? It really makes you look at the world differently, doesn't it? Thank you so much for joining me for this explainer. Keep asking those big questions, and I'll see you next time.